We're going to talk about inverses of functions today. Now, earlier we talked about what a relation is and what a function is. A relation is something that pairs one group to another. So you might have elements of one group paired to elements of another group. And when those elements, say x's from a domain, are paired to the y's from the range, then you may get a function if each x only goes to one y. Well, an inverse then is to reverse that pairing. So what was kind of x going to y is now going to be your y going to x. Only in this inverse, if it's a function, then this is going to be an inverse function. So your new x, it will be your old y, and your new y will be your old x. Now, in order to be an inverse function, it must also then satisfy the requirement of being a function, which means that your inverse relation, each of the new x's has to go to just one y. So let's actually dive into this a little bit more. Let's talk about mapping first. Here I've got a function. I've got -4 in the domain going to -2, 0 going to -3, 1 going to 2, and 4 going to 1. Note here that the numbers in this domain are separate from the numbers here in the range. Remember that domain is kind of our x's, right? Left to right, range is our y's, up and down. So this 1 is not the same as this 1 in the range. Now what's important to note here is that this is a function. Right, this -4 only goes to one element in the range, -2. This 0 only goes to one thing, -3. 1 only goes to 2. 4 only goes to 1. And when I reverse this, so -2 will now go to -4. Here I've got that mapped over here. -3 goes to 0, 2 goes to 1, and 1 goes to 4. All I've done is taken each of these and reversed them. I've gone from left to right and now right to left, just written it such that this is the new domain and this is the new range. And I'm asking, is this a function? Well, yes, this is a function because it matches what the requirements of a function are. Each element in the new domain is only paired to one element in the new range. -2 is only paired to one thing, -4. -3 is only paired to one thing, 0. 2 to 1, 1 to 4. And in fact, this is also a 1-to-1 function because each element of my x is paired to each element of my y 1-to-1. There's only one x for every one y, and vice versa, only one y for every one x. So not only is the inverse a function, but it's also a 1-to-1 function. Whereas down here, I've got -4 to -2, 0 to -3. I've got 1 to 2, and 4 to 2. Now this is still a function because -4 is only paired to one element in the range. It's only going to one y. -4 is going to -2. 0 is still only going to one thing, -3. 1 is still only going to one thing, 2. And 4 is only going to one thing, 2. So this itself is a function. Is the inverse then. When I reverse these pairings from -4 to -2, now -2 to -4, 0 to 3, -3, -3 to 0. However, here, 2 is going to both 1 and 4. So this inverse is not a function. Why is it not a function? Because each of these values in the domain can only have one pairing to one value in the range. What this is saying is if I plug in 2 to whatever this inverse would be, I would end up with two possible answers, 1 and 4, which makes it not a function. Okay, I can only have one possible answer. That's different than over here because when I plug in 1, I get the answer 2. That's only one answer. When I plug in 4, I get one answer. Again, this 2. Here, I plug in 2, and I get more than one answer. So this is not a function. I would say no. The inverse is not a function. And if it's not a function, certainly it's not a one-to-one function. What about graphically? Let's say I've got this here. These are the points -1, 1, so -1, 1 is right here. I've got 1, 3, so over 1, up 3, right here. I've got 0, 5, 0, 5 is right here, and 3, 6, so to the right 3, up 6, this point right here. What if I were to reverse all of these relations? So I've got -1, 1. If I were to reverse this, this would be 1, -1. 1, 3 would be 3, 1. 0, 5 would be 5, 0. And then 3, 6, this would be 6, 3. Now what happens if I were to take these new points and plot them on the same graph here? Let's see, 1, -1. So 1, -1 would be right here. 3, 1, 3, up 1. 5, 0, 5, 0 right here. And 6, 3, 6, and up 3, 1, 2, 3. Well, what do we notice? These points right here are symmetrical. They're equidistant from this diagonal line, and they're symmetrical about this diagonal line. What you see on this side, you will find over here, as if it were mirrored. And what is this line? This line is y equals x. Now I want you to remember this as we continue on throughout this lesson here, that these points ended up being symmetrical about this line y equals x when I took the inverse of these points. All right, how to find the inverse of a function then? Let's say I give you some function. What are the steps that you need to take in order to find the inverse? Well, there's 3 steps. Step 1, replace f of x with y. You may remember that function notation, f of x is just really kind of fancy for y. So I'm just going to replace it with y so that way I can kind of work with it a little bit better. Step 2, I'll solve for x. Now, we may have multiple kind of smaller steps within this bigger step 2, but I want to get x alone. X equals whatever it is. Then step 3, once x is solved, this is actually taking your inverse. You're going to take your x, you're going to take your y, and you're going to swap them. So what was x becomes y, what was y becomes x, and then finally, you'll replace that newer y. We're going to go back to function notation, but this time we're going to say f to this like -1 of x. And what this actually means is f inverse of x. This is the inverse of function f. Let's do a couple examples. I've got 3x plus 4 here. I want to follow these 3 steps. Step 1, replace f of x with y. So this will be y equals 3x plus 4. Step 2, let's solve for x. So this means get x alone. Right now, x is being multiplied by 3, and I've also got this plus 4 here. So let's begin by subtracting 4. This gives me 3x equals y minus 4. And then let's divide by 3. So I've got x equals y minus 4 over 3. Okay, now I've got x solved. So step 3, once x is solved, I'm going to swap x and y. So what was x becomes y. What was y becomes x. This is going to be y equals x minus 4 over 3. And then let's change this back to function notation. This function is the inverse of f. Okay, it's the inverse of function f. Therefore, I'm going to call it f inverse of x. And this is actually x minus 4 over 3. Okay, so the original function is 3x plus 4, and the inverse is x minus 4 over 3. And if I were to graph these two, I would get something like this. And what's notable is that this dashed line, that's y equals x again. So I saw this with points, and I'm seeing this now with an entire line. They're going to be symmetrical about this y equals x. Let's do another one. F of x equals 2x minus 2. 3 steps. Isolate, or no, not isolate. We're going to change the f of x to y, and then we're going to then solve for x, so isolating x, and then changing x and y, swapping them, and seeing what we get for our inverse. So y equals 2x minus 2. So now solve or isolate x, so add 2 to both sides. And I'll get 2x equals y plus 2. And then divide both sides by 2. Okay, so this gives me x equals y plus 2 over 2. X is solved, or sometimes I say x is isolated. And once I'm at this point, I'm going to swap x and y. So x becomes y becomes x. Y equals x plus 2 over 2. And this, then, changing back to function notation, is going to be f inverse of x equals x plus 2 over 2. Now, worth noting here, sometimes your textbook or your teachers, professors might want you to go a step further in saying, well, is there something else that we can do here? Remember that x plus 2, all of x plus 2 is being divided by 2. So we could say that this is, or f inverse of x equals x over 2 plus, and then 2 is being divided by 2 as well, but 2 divided by 2 is 1. So each of these, whichever one is technically, they're both correct. Just do whichever your teacher or your professor wants you to do. And then, of course, when I graph these, they're again symmetrical about that y equals x line. And now that keeps coming up, being symmetrical about this y equals x. So what we're going to do next is I'm going to talk a little bit more about that and what's called something called function composition. Okay. Function composition, you may have done this before in a previous class, where this is essentially saying, instead of evaluating for a number, instead of saying f of 2, where you're plugging in 2 into function f, you might plug in f of g of x, meaning you're going to take whatever function g is, and you're going to plug that into your function f rather than just a regular number. Okay, let's see what happens when I do this using inverses. In the first example, we were given this function, f of x equals 3x plus 4, and we found the inverse. The inverse was f inverse of x equals x minus 4 over 3. This is asking, what is f inverse of f of x? So it's asking me to take f inverse, use that as a base, and then plug in my other function. So plug in f of x, which is 3x plus 4. Let's see what that looks like. Firstly, my base. My base here is going to be f inverse. Is x minus 4 over 3. Now what this is doing, this is saying x minus 4. I want to replace this x with f because I'm plugging in f into my f inverse. So that means instead of x minus 4, I'm going to have 3x plus 4, and then still this minus 4, and then still over 3. So I just replaced x here with f. 3x plus 4 here, then minus 4 over 3. Let's simplify this. 4 minus 4, that's going to go to 0. And I'm left with 3x over 3. So this is f inverse of f of x. This is 3x over 3. 3 divided by 3, that's going to divide out. F inverse of f of x equals x. All right. Interesting. Well, first of all, this is all function notation, right? What is this really just really fancy for? If I had just a graphing calculator and I needed to plug in this here equals x, technically this would just be y. Y equals x. And there's your diagonal line in those graphs. There's your line of symmetry. In fact, anytime that you use function notation with a function and its inverse, you will always get x. When you plug in one function into another, if they are inverses, you will always get just x. If you get anything else, assuming that you've done it correctly, then they're not inverses. Okay, let's do this one more time with the other two that we got. In example B, we got these two. We got f of x, my original function was 2x minus 2, and my inverse that I found was x plus 2 over 2. And what I'm going to show you is I can do this with f being the base as well as f inverse being the base. So it really doesn't matter which way you plug in one function into another. If they're truly inverses, you should get x, just x. So let's, on the left side here, say let's use f of x as a base. Okay, and over here we'll say let's use f inverse of x as a base. So if f of x is a base, then I've got 2x minus 2. And instead of x, I'm going to plug in 2 times, and I'm going to plug in x plus 2 over 2. But I'll still have minus 2 at the end. Okay, for this one, I'm going to use x plus 2 over 2 as a base. And instead of x, I'm going to plug in f. So on top here, I'll have 2x minus 2. But I'll still have plus 2 and all over another 2. All right, this one here, I'm multiplying this by 2. I know that this fraction here, I've got a 2 in the denominator. These will end up dividing out. So I've got x plus 2 minus 2. And 2 minus 2, that's going to go to 0. So we'll subtract those out, leaving just x. Okay, over here, on the top, I've got negative 2 plus 2. So that's going to go to 0. And this leaves me with 2x over 2. Of course, 2's here are going to divide out, leaving just x. So it does not matter which one of these you use as a base and then plug in the other two. If they are inverses of each other, you will always get back just x when using function composition.